Hi everyone, I'm Julia, the chemistry tutor, and today I am going to talk about redox reaction basics. Okay, I am not going to balance redox reactions in this video. If you're in general chemistry, you will need to balance redox reactions. I will do another video for that process. This video is just about the basics of redox reactions. Okay, so let's get started. Okay, so we're looking at my information sheet for redox reactions. So first, let's just talk about what redox is. Redox is oxidation and reduction. Okay, and so we just shorten that to redox, reduction, oxidation. Okay, and we'll talk a little bit deeper about this in a minute, but oxidation is you lose electrons, and reduction is gain electrons. Okay, we'll talk more about that in a minute, but that's what redox is it's oxidation and reduction. Okay, so when we're looking at this, when you're doing a redox reaction, you have to assign oxidation numbers to all of the elements to see from reactants to products what lost electrons and what gained electrons. So you can see which one was oxidized and which one was reduced. Okay, so when assigning oxidation numbers, these are your rules. Okay, so if it's elemental, if it's just an element, its oxidation number is 0. It has 0 oxidation. There's no charge going on. Okay, so a metal just sitting there all by itself, okay, is 0. And remember, diatomics are also elemental. Those are 0. Okay, so this is when it's just there all by itself. And by the way, you might see things like S8. That is elemental. If it's just one type of element there, that is elemental, no matter how many there are. You could have like P4. Okay, I think I've seen P10. Okay, so it doesn't matter how many. If there's only one element there and there's no charge, that is elemental. Okay, one type of element, I should say. Okay, so monoatomic ions is just one ion sitting there by itself. Okay, their oxidation number is whatever their charge is. So, for example, magnesium ion, his oxidation number is +2. Phosphide ion, his oxidation number is -3. Okay, if I had sulfur, -2, his oxidation number is -2. So if it's just a single ion, single atom ion, monoatomic, not your polyatomics, right? Like these guys down here are polyatomics. Okay, your monoatomics are just whatever their charge is. That's their oxidation number. Okay, so now we're talking about if it's in a compound. Both of these, they're just sitting there by themselves. Okay, but now if we're talking about in compounds, your most important rule is all of your oxidation numbers. Once you assign them all, they must add up to the charge on the compound. Okay, so like if I had SO4 -2, the sulfate ion, for all of the atoms on there, for all 4 of my oxygens and my 1 sulfur, those have to add up to -2, the charge on that polyatomic ion. Okay, the charge on the compound. Okay, if I had carbon dioxide, there's no charge. So the oxidation numbers for the 2 oxygens and the 1 carbon must add up to 0 because there's a 0 charge on that compound. Okay, so all of your oxidation numbers, when you add them together, they need to equal the charge on the compound. Okay, so the rest of these rules, you pretty much know all of these rules. You actually already know that elements don't have any charges, that monoatomic ions are whatever their charge is. Okay, but oxidation numbers isn't necessarily the charge. It's what is the perceived charge on that element, okay? Because it's going to be different based on what you're talking about, okay? So number 1 rule, oxygen is -2 when it's in a compound. Remember, these are in compounds. If oxygen is O2, that's an element. That's elemental, and its oxidation number is 0. But if oxygen is in a compound with other elements, it is -2. And you know that because oxygen is -2 on the periodic table. Okay, if you're in general chemistry, you will have to pay attention to if it's in a peroxide, it's -1. and if it's with fluoride, it's +1. And the reason for that rule is because fluoride is always -1. Okay, unless it is elemental fluoride, your diatomic fluoride, that is 0. But if fluoride is in a compound, it is -1. So if oxygen is with fluoride, and we know fluoride is -1, the oxygen has to be a +1. Okay, so that's kind of weird. But if you're in allied health chemistry, none of that matters. Okay, we're not going to worry about that. Okay, so allied health chemistry, as far as you're concerned, oxygen is -2 in a compound. Okay, hydrogen is +1. You already know that because on the periodic table, hydrogen is in group 1, it's +1. Okay, in general chemistry, if it is with a metal like sodium, it has to be a -1 because sodium, group 1, is always +1. That's our next rule. Group 1 metals in compounds are always +1. And you know that rule. You know group 1 metals are +1. So in this case, for that compound to equal 0, the hydrogen has to be a -1. Okay? But in allied health chemistry, you typically do not need to worry about that. In general chemistry, you will need to worry about that. Okay? Okay. Excuse me. So I just talked about that group 1 metals are +1. Group 2 metals are +2. You already know that. And we talked about fluoride is -1. Okay, so now let's talk about in binary compounds. Okay, binary compound, binary meaning two different types of atoms. So two types of elements. Okay, and nonmetals because they are covalent. So a binary compound is a covalent compound with only two types of elements in it. Okay, so when we look at those, only two types of atoms, okay, the more electronegative atom, its oxidation number is the same as its charge on the periodic table. Okay, so, well, these can be also your polyatomic ions. Now that I think about it. Okay, because the CN minus, the cyanide there, okay, neither C nor N are in our rules up here. We usually know from oxygen and hydrogen. Okay, there's no oxygen or hydrogen in there. So this is binary, two types of elements in there. And so we say the one that's more electronegative gets its number from the periodic table. So nitrogen, remember, electronegativity gets larger as you go up and to the right on the periodic table. So nitrogen is to the right of carbon. So nitrogen gets the -3, like the periodic table. In order for this whole thing to equal the -1, the carbon has to be a +2. Okay, so binary compounds, the more electronegative atom gets its charge from the periodic table, its oxidation number. Okay, so for example, here my SCl2. If you're looking at the electronegativity of those on your periodic table, sulfur is here and chlorine is to the right of it. So chlorine is more electronegative. So the chlorine gets the -1. And so I have a -2 from chlorine, right? Because I have two chlorines, so a -2. And so I have a +2 for the sulfur in order for the whole thing to equal 0. Okay? So in binary compounds, two types of atoms, okay, if it doesn't have oxygen or hydrogen in it, then the more electronegative atom gets its oxidation number is its charge on the periodic table. Okay, so those are our rules for assigning oxidation numbers. Okay, so now when you're working with a polyatomic ion, okay, my suggestion is that you pull the polyatomic ion out of the compound and do it by itself. Okay, so we have Okay, you know the charge on your polyatomic ion. So for example, if we're doing manganese sulfite, okay, so manganese sulfite. Okay, I'm going to pull that sulfite out all by itself. And you know from nomenclature, the charge on sulfite is -2. Okay, so if I look at that, okay, here we go. This is where we're looking at, we didn't do any of these earlier. So now I'm going to talk about how we figure out that sulfur. Okay, so we know oxygen is -2. Okay, do you agree with me that I have -6 from the oxygens? Okay, I want to keep -2 because of that charge up there. I want to keep 2 of those. So in order to balance out the negatives that I have up there, I need a +4, right? Because +4 and -6 is going to equal my -2 that I need. Okay, and so I'm going to divide that +4 by the 1 sulfur that is there. If you had 2 sulfurs, you would divide it by 2. If you had 3 sulfurs, you would divide it by 3. So I'm dividing by the 1 sulfur. So that sulfur is +4. So we know the sulfur is +4. Okay, now to determine your manganese, it's just exactly as if you were naming this compound. It's manganese. You know he's a variable charge, so we'll put parentheses for the charge. And SO3 is sulfite. So most of your instructors, we swap and drop. We swapped down to get the charge, to get the subscript. So we're swapping them back up to get the charge. So that's manganese 3. So you know the charge on the manganese is +3. Okay, and so I did this saying, okay, I know all of my oxidation numbers needed to equal the -2. We're going to do a lot more practice with that in a minute, okay? But that was just an example where you pull your ion out by itself, and it doesn't matter that there's 3 of them there. All 3 of those sulfites, all of the oxygens have the same oxidation number, all of the sulfurs have the same oxidation number. So you only need to calculate the oxidation numbers for one of the polyatomic ions, and the rest of them are the same. Same with those manganeses. It doesn't matter that there's 2 manganeses there. Both of them are a +3. Okay? Okay, so here are some basic things that I said we would talk about, the gaining and losing of electrons. Okay, our gaining and losing of electrons. Okay, I remember this by the saying oil rig. Okay, oil rig. There's another saying, I'll talk about that in a minute. But oxidation is loss of electrons. Reduction is gain of electrons. Okay, and so if you lose electrons, you're losing negative. So you're going to get more positive. Okay, so oxidation, losing electrons, gets more positive. Okay, and so by more positive, I don't mean it becomes positive. It just gets more positive. So like I say here, for example, -7 to -3, if we're looking at the number line, and here's 0, here's -7, here's -3, that is going in the positive direction. It is getting more positive. Okay, because that's how we're going to decide who's oxidized or reduced, is by looking, did it get more positive or did it get more negative? Okay, if you are reduced, gaining electrons, you are gaining negatives, so you are going to get more negative. You don't necessarily become negative. Okay, so reduction, it is gaining electrons, it gets more negative. So for example, +6 to 0 is more negative, because on the number line, here's 0, here's +6, you're going in the negative direction. You are getting more negative. Okay, same thing, positive 6 to positive 2. Okay, you're still moving in the negative direction. You're getting more negative. And that is why we call reduction reduction, is because your oxidation number is reduced. It gets more negative. It reduces. That's why reduction is reduction. Okay, so we hit those. Oh, Leo the lion goes grr. Okay, so I like the oil rig. That's just how I learned it. But there's another one that is Leo the lion says grr. And that is lose electrons, oxidation, gain electrons, reduction. But it's the same exact thing. Oxidation gets more positive because you're losing electrons. Reduction gets more negative because you're gaining electrons. Okay, so you could use either one of those sayings to remember it. It's totally up to you. Okay, so now we'll talk about the agents, okay? So the oxidizing agent is the compound that was reduced, okay? And up here, you see I have only the element that changes charge is oxidized, and now I have the entire compound. Okay, so for example, if we were going from MnO2 to Mn plus 2, okay, my oxygens are -2. So I have -4 from oxygens. I don't want to keep any of them, right? Because my charge is 0 up here. So I need a +4 divided by the 1 manganese that's there. So manganese is +4. This is a monoatomic ion, so its oxidation number is its charge. So that got more negative. That was reduced. Okay, because my oxidation number reduced. Okay, so in this case, manganese was reduced. MnO4, the entire compound, the whole agency, was the oxidation. Oh, yeah, oxidation, oxidizing agent. Sorry, I got lost in my words there. Oxidizing agent. Okay. So it feels really weird, and students are like, oh, it's just the opposite. And it is. It's just the opposite of what happened to it. Okay. But if we were doing a reaction where basically it always happens together, if manganese was reduced in that, then there was another compound in there that got oxidized. Okay. And so if manganese was reduced, the MnO4, by the manganese gaining those electrons, it is the agent of the other one's oxidation because it allows the other one to lose those electrons by itself gaining them. So whoever's reduced allows the other one to be oxidized. He is the agent of the other one's oxidation, the oxidizing agent. Okay, and then same thing with reducing agent by becoming reduced. Oh, well, it was the same what I was talking about. Oxidized by losing electrons. It allows the other one to become reduced. Oh, I said that backwards. The agent is the one that got reduced. Being reduced allowed the other one to be oxidized. The one that was oxidized is the reducing agent because it allows the other one to be reduced. Okay. So those are our basic rules for redox reactions, for redox, how to assign those oxidation numbers, right? How to tell if it was oxidized or reduced, and how to tell if it's an oxidizing or reducing agent. So now we're going to do some practice with those. Now we're going to practice assigning oxidation numbers. So if you did not write those rules down when I gave them earlier, maybe rewind the video, go back and write those rules down so you have them in front of you, because I'm not going to swap back and forth on the screen between everyone. Okay, So chlorine, diatomic chlorine, is elemental. Its oxidation number is 0. Chloride, that's a monoatomic ion, right? So that's a monoatomic ion. So it is whatever its charge is. So it's -1. This is sodium sitting there all by itself with no charge on it. That is elemental sodium. It is 0. Here is sodium sitting there with a charge on it. That is a monoatomic ion. Its oxidation number is its charge. Okay. So now on this one, potassium chloride, potassium is a group 1 metal, right? And we know group 1 is always +1 in a compound. So if potassium is a +1, for that whole thing to equal 0, chloride has to be a -1. Okay. Chloride is not always -1. The chlorine, not always -1. You might feel like it is, but it's not. I'm actually going to pop back over to this screen and explain that for a second. Okay, so let me do this real quick. If I have... Okay, on this one, monoatomic ion, his oxidation number is -1. But now when I look at these ones up here, okay, I know oxygen is -2. So I have -8 from those oxygens, right? Because I have 4 oxygens. 4 times -2 is -8. I want to keep a -1 because I have that charge there of -1. Okay, so I need a +7, right? Because +7 plus -8 equals that -1 we're looking for. Okay, divided by the 1 chlorine that's there. So that chlorine is +7. Okay, and on the periodic table, you're thinking, well, chlorine is -1. Why is it +7? It's because when we did the Lewis dot structures, okay, oxygen is more electronegative than chlorine is. Okay, oxygen is 3.5 and chlorine is 3. So oxygen pulls those electrons away from the chlorine. Okay, so the oxygen, those electrons are a little bit closer to the oxygen than to the chlorine. So chlorine has a perceived, it feels like it has a +7 charge. That's what oxidation numbers are. So they are not necessarily what the charge is from your periodic table. It is what the perceived charge is when it's bonded to other atoms and those other atoms are pulling electrons away from it. Okay, it gets a perceived charge. Okay, if we're looking here at chlorite, right, we have a -6 from the oxygens. We need to keep one of them. So we need a +5 divided by the 1 chlorine that's there. That one is +5. Over here, I'm running out of space there. So over here for this guy, we know that we have a -4 from the oxygens because oxygen is -2 and we have 2 of them. We want to keep a -1, so we need a +3 divided by the 1 chlorine that's there. This one is +3. If I had the ClO, we know we have 1 oxygen, so we have a -2 from the oxygen on this guy right here. We want to keep a -1 because of the charge on the compound, so we need only a +1 divided by the 1 chlorine that's there. That one is +1. And this one, being a monatomic ion, is -1. Okay, so you see the more oxygens that are on that chlorine, the more electrons are pulled away, the more positive it feels like it is, the more positive it is perceived to be. Let me explain that dividing by the one chlorine. If I had S2O3, -2, okay, I know that we know oxygen is -2, okay, so we need to figure out the sulfur. So I have a -6 from those 3 oxygens, right? I want to keep a -2 from the charge. So I need a +4, because +4 and -6 equals that -2 we're looking for. But because now I have more than one of those atoms there, each sulfur is going to bring an equal charge. So I divide by the 2 sulfurs. So each of those sulfurs is a +2. If I had Cr2O7 dichromate, okay, we know that oxygen is -2, and we have -14 from the oxygens. We want to keep a -2, so we need a +12 divided by the 2 chromates that are there. Each chromate is a +6 to give us the total +12 we need. Okay, so when we're saying that that's what their oxidation number is, right here, because that's essentially a monoatomic ion, that chloride, he has his charge on the periodic table. It's because potassium is +1. The chloride has to be a -1. Okay, so on this next one, we know in a compound, hydrogen is +1. From 2 hydrogens, we have a +2, so that sulfur has to be a -2. It happens to be the same as the periodic table, but it's not always going to be that way. The thing to think about is that sulfur is really a monoatomic ion. Okay, so my calcium oxide, we know calcium is group 2. They are always +2. We know oxygen in a compound is -2. Didn't even have to do any math on that. Here with this, hydrogen in a compound we know is +1. Oxygen in a compound is -2. No math involved. Okay, now we've got nitrate. So I have a -2 for my oxygens. I know that. So I have a -6 from my oxygens. I want to keep a -1. I need a +5 divided by the 1 nitrogen. Nitrogen is +5. My NO2, we know oxygen is -2. I have -4 from my oxygens. I want to keep 0, so I know I need a +4 divided by the 1 nitrogen. Nitrogen is +4 in that case. All right, now the dichromate that we just did. So we know oxygen is -2. We have -14. Here, I'm going to change my size of my pen here. Let's make it a little bit smaller. Okay, so I have -14 for my oxygens. I want to keep -2, so I need +12 divided by my 2 chromiums that are there. Each one of them is a +6. O2, that's elemental oxygen. That is 0. NH3, in a compound, we know hydrogen is +1. So I have a +3 for my hydrogens. I don't want to keep any because there's no charge. So I need a -3 divided by the 1 nitrogen that's there. So nitrogen is, -3 in this case. Okay. So see how my nitrogens, Here is a positive 5, here is a positive 4, here is a negative 3. It all just depends on what they're bonded with and the electronegativity, who's pulling these electrons away and who has the perceived charge. Okay, this one here is one of them that Gen Chem I talked about. If hydrogen is with a metal, because we know group 2 is positive 2, those hydrogens have to be negative 1. Okay, so remember, hydrogen with a metal is negative 1. Okay, now sulfate, looking at that guy there, we know that oxygen is negative 2 in a compound. So I have a negative 8 from my oxygens because I have 4 of them. I want to keep a negative 2. So I need a positive 6 divided by the 1 sulfur. Sulfur is positive 6. I'm going to go ahead and finish all this practice because I think it's really good for you. Okay, on this one, sodium is group 1 metal. We know is positive 1. Oxygen in a compound is negative 2. Here, we know hydrogen is positive 1. We know oxygen is negative 2. So now we're looking at, we have a negative 6 from the oxygens. We have a positive 1 from the hydrogens. So we really have a negative 5 to compensate for. Okay, so we need a positive 5 because we don't want to keep any of them. There's no charge, right? So we don't need to keep any, keep 0. Okay, so that 5 divided by the 1 nitrogen that's there. So nitrogen is positive 5. Here, we know calcium is a group 2. He's positive 2. So if I have positive 2 for my calcium, each of those chlorides needs to be a negative 1. Does that make sense? Because I have a positive 2. I want to keep 0. So I need a negative 2 divided by the 2 chlorides that are there. Also, you could look at that as chloride is a monoatomic ion. So for phosphate here, we know oxygen is negative 2. We have a negative 8 from our oxygens. We want to keep a negative 3. So we need a positive 5 divided by the 1 phosphorus that's there. He is positive 5. For my MnO2, we know oxygen is negative 2. So we have a negative 4 from our oxygens. We want to keep 0. So we need a positive 4 divided by the 1 manganese that's there. He is positive 4. Here we know potassium is a group 1. He's positive 1. Oxygen is a negative 2. Okay, so now, and I did this up here, but I didn't really talk about it. I did it with this one where we have to look at our negatives and our positives before we decide how many we need. Okay, so we know that we have positive 3 from potassium because there's 3 of them. We know that we have a negative 8 from our oxygens. So we have a negative 5. Okay. We don't want to keep any of them because there's no charge on this. Keep 0. So we need a positive 5 to compensate for that negative 5. So phosphorus is a positive 5. On this one, we know oxygen is negative 2. So we have a negative 6 from our oxygens. We don't want to keep any of them because there's no charge on the compound. So we need a positive 6 divided by the 2 ions that are there. Iron is positive 3. Here, potassium group 1 is positive 1. Oxygen is negative 2. I have a positive 1 from my potassium. I have a negative 4 from my oxygens. So I have a -3. I don't want to keep any of them because I have no charge on that compound, so I need the +3 divided by the 1 nitrogen that's there. So nitrogen is a +3. On the next one, N2, that's diatomic. That's your elemental nitrogen. So that's 0 because elements are 0. Here I have a monoatomic ion, +3. This one is a peroxide. Okay, this is for general chemistry. That's hydrogen peroxide. And we know that hydrogen is +1. So I have a +2. I need a -2 divided by those 2 oxygens that are there. This is when oxygen is -1. Okay, is in a peroxide. And again, if you're in allied health chemistry, you probably don't need to worry about that. But you want to recognize this is typically the peroxide we talk about. And hydrogen is only -1 when it's with a metal. So hydrogen with oxygen is +1. That means oxygen in this case has to be a -1. Okay, so here on the next one, hydrogen we know is +1. Oxygen is -2. So I have a +2 for my hydrogens. I have a -8 for my oxygens. So I have a -6. I need a +6 divided by the 1 sulfur that's there. +6. Okay, here we know hydrogen is +1. And do you recognize that this is ions? So we're pulling out that polyatomic ion, the NH4+. This is a monoatomic ion, so he's -1. Oh, I put my +1 with nitrogen. Hydrogen's +1. So if we're looking at that NH4, I have +4 for my hydrogens. I want to keep a +1. So I have a -3. I need the +3 divided by the 1 nitrogen that's there. It's +3. Oh, -3. Sorry. Whoops. I got my signs wrong there. Here I have a +3. I need a -3 divided by the 1 nitrogen that's there. Nitrogen is -3 in this case. Sorry about that. Okay, on this one, oxygen we know is -2 in a compound. If oxygen is -2 for that whole thing to equal 0, iron has to be a +2. For this one, we know oxygen is -2. So we have a -4 from our oxygens. We don't want to keep any of them. So we need a +4 divided by the 1 silicon that's there. It's +4. Okay. So I hope that kind of helped you figure out how to determine your oxidation numbers. We'll be doing more of those because we have to do a bunch of them pretty soon here. And when the next step we're doing, we're going to be doing that to do what we're doing. Okay, so let's practice with these couple ones. Okay, so now I have an actual chemical reaction that happens. And so now we're going to be able to decide how they changed charge and if they were oxidized or reduced. Okay, so the first step is to do those oxidation numbers like we were just doing. So here calcium, that's elemental calcium, that is 0. Hydrogen in a compound is +1, oxygen is -2. Calcium here in a compound, group 2 metal, +2. We know oxygen is -2, and elemental hydrogen, diatomic hydrogen, is 0. So now when we look from one side to the other, calcium got more positive, right? 0 to +2 is more positive, meaning that was oxidation. And my hydrogen from +1 to 0 got more negative, that was reduction. So my element oxidized was calcium. My element reduced was hydrogen. Okay, each individual hydrogen was reduced. Okay, so now on this one, elemental hydrogen, 0. Elemental oxygen, 0. Hydrogen in a compound, +1. Oxygen in a compound, -2. So from one side to the next, my hydrogen got more positive, so he was oxidized. My oxygen got more negative, he was reduced. Okay, and we're looking at element, the actual element, and hydrogen was oxidized. That is elemental hydrogen. Oxygen was reduced. That was elemental oxygen. All right, hold on a second here. Okay, so this one's in a little bit of a different format, but it gives us all of our information. It's telling us everything that we need, or it's giving us blanks for everything we need to identify. Okay, so we need to give the oxidation number for each element in the compound. So when we're looking at that potassium permanganate, if we look up here, potassium permanganate, we know that potassium is +1 because he's a group 1. We know oxygen is -2. So we need to figure out that manganese. Okay, so if I'm looking there, I have a +1 from my potassium. I have a -8 from my oxygens. So I have a -7. I don't want to keep any of them because there's no charge on that compound. So I need a +7 divided by the 1 manganese that's there. Manganese is +7. I'll go ahead and write that there just because. Okay, now I'm looking at the NO2, or the NO, sorry, we know oxygen is -2. Okay, so if my oxygen is -2 and the whole thing equals 0, there's no charge up here, nitrogen has to be a +2. Okay, and my MnO2, we know the oxygen is -2. So we have -4 from those 2 oxygens. We don't want to keep any of them because there's no charge on the compound. So we need a +4 divided by the 1 manganese that's there. That manganese is a +4. Looking at potassium nitrate, we know potassium is group 1. He's +1. Oxygen is -2 in a compound. So from that one, we have a +1 from the potassium. We have a -6 from the oxygens. So we have a -5. We need a +5 divided by the 1 nitrogen that is there. So that nitrogen is +5. I'm going to erase all this to give us some room. Okay. So, oops. So you're not always going to have all of these blanks. You're going to have more like what I was doing earlier, where you're just going to have it and you're going to have to do it just right there in the equation and figure it out. If you have these blanks, I guess you can figure out by looking here that my potassium did not change at all. My oxygens did not change. So we're looking at manganese and nitrogen. Okay, and so my manganese from the KMnO4 to the MnO2 got more negative, right? -7 to -4 is +7 to +4 is going negative on the number line. So that was reduced. Okay, and my nitrogen from one side to the other got more positive. That was oxidized. Okay, make some room there. So that was oxidized. So the element oxidized, the element was nitrogen. But remember, the oxidizing agent is the entire agency. The element that was reduced was the manganese. But the agent is the entire agency. Okay. And what you want to look at here is I want you to recognize all of your answers are reactants. Okay, your answers will always be the reactants. The products are only there to see how the charge changed. Okay, how your oxidation number changed. Your answers on these will never be the products. They will always be the reactants. Okay. And let's see, for general chemistry, you're actually going to be balancing redox reactions, and that'll tell you how many electrons exchanged. But here, if we had to look at this, we went from 7 to 4, so that was a difference of 3 electrons. And we went from 2 to 5, a difference of 3 electrons. So 3 electrons were exchanged. Okay. All right, let's look at this next one. So I've got the iron 2 oxide. So here we know oxygen is -2. So we have a -6 from the oxygens. We don't want to keep any of them. So we need a +6 divided by those 2 irons that are there. So each iron is +3. Carbon monoxide, we know oxygen is -2. For that whole thing to equal 0, carbon has to be +2. Over here, I have elemental iron, that is 0. And in carbon dioxide, we know the oxygen is -2. So I have -4 from the oxygens. I don't want to keep any of them because there's no charge on that compound up here. So I need a +4 divided by the 1 carbon that's there. So that carbon is +4. Okay, so now if I look from one side to the next, okay, oxygen is -2 all the way through. But iron got more negative. -3 to 0 is more negative. That reduced, that was reduction. Carbon got more positive. That was oxidation. Don't have enough space there. Okay, so the element that was oxidized is, oh, there we are, carbon. And the oxidizing agent is the entire agency. Oh, wait, I have those wrongs. Hold on. They have these backwards than what I'm thinking. Okay, hold on. Your oxidizing agent, I got these wrong up here. Let's go back and look at that. So the element that was oxidized was nitrogen. So that compound is the reducing agent. The element that was reduced was the manganese. So that compound is the oxidizing agent. Whew, that was worded backwards than what I'm used to. Okay, so we said our carbon was oxidized, making that compound the reducing agent. My element reduced was the iron, making that compound the oxidizing agent. Ooh, I'm glad I caught that before we went too far. Okay, so now here looking at these, for the sulfurous acid, we know hydrogen is +1 and oxygen is -2. So we have +2 from our hydrogens. We have a -6 from our oxygens. So we have a -4. We don't want to keep any of them because there's no charge on that compound, right? So we need a +4 divided by the 1 sulfur that's there. +4. Okay, we're looking at this reaction up here. So we just did that. This is elemental manganese, 0. Okay, here, my hydrochloric acid, We know the hydrogen is positive 1. In order for that whole thing to equal 0, the chloride is negative 1. Plus, if you look at that as an ionic compound, that's a monoatomic ion. Okay, so up here on this side, I have elemental sulfur. That is 0 for my manganese chloride. Okay, we know these are monoatomic ions. Okay, also you could look at it as binary compound. Chlorine is more electronegative than manganese, so he gets his number from the periodic table. He's negative 1. Okay, so if I have a negative 2 from those two chlorides, sorry about that, then we know the manganese has to be a positive 2. Right, because we could do that like we did earlier. I have a negative 2 for my chlorides. I don't want to keep any of them because there's no charge on that compound. So I need a positive 2 divided by the 1 manganese that's there. He has positive 2. Okay, now when I look at water, we know water, H in a compound is positive 1. Oxygen in a compound is negative 2. Okay, so we have all of our numbers here. Now we need to decide. So oxygen was negative 2 all the way across. Hydrogen was positive 1 all the way across. Your hydrogen still positive 1. So here sulfur got more negative. Reduction. Oh, your chlorine was negative 1 the whole way. Manganese got more positive. Oxidized. So the element that was oxidized was the Mn, and that entire compound, which was just the Mn, is the reducing agent. The element that was reduced was the sulfur, and that entire compound is the oxidizing agent. And if we look at how many electrons were exchanged, this one exchanged 4. And this one exchanged 2, except there were 2 manganeses there. Right? There's 2 manganeses on each side, so that's my 4 electrons. So 4 electrons were exchanged. We did not look at that up here. Up here, iron exchanged 3, carbon exchanged 4. And so what you would technically do is if you were balancing redox reactions, you would be multiplying one of them by 4 and one of them by 3. It would be 12 electrons. Okay, you're just multiplying those together by each other. Okay, and down here, because I had 4 for this and 2 for this, for the manganese, right? They both go into 4, so it was 4. It's your highest number. It's okay. Up here, they were both 3 and 3, so it was just 3. Here, where was I there? Because it was a 3 electrons and 4 electrons, and they don't, one of them doesn't divide evenly into the other. You multiply those by each other. It was 12 electrons. Okay, so let's do a couple more of those. Just doing it like that. Okay, so here, I'm looking at this reaction up here. So I have lead, that is elemental lead, it is 0. Here in the lead O2, we know oxygen is negative 2. So I have, I don't know if you can see that that lead is a positive 4, but I have negative 4 from my oxygens. I don't want to keep any of them because there is no charge on the compound. So I need a positive 4 divided by the 1 lead that is there. That lead is positive 4. Hydrogen we know is positive 1. Oxygen is negative 2. I have negative 8 from my oxygens. I have positive 2 from my hydrogens. So I have negative 6. I don't want to keep any of them because there's no charge on the compound. So I need positive 6 divided by the 1 sulfur that is there. That sulfur is positive 6. Over on the other side here, okay, we know oxygen in a compound is negative is, sorry, -2. I don't know why I made that 0. Oh, but look at what we're doing here. This is a covalent, a polyatomic ion. We're going to pull that out by itself. Okay, so I have -8 for my oxygens. I want to keep -2. So I need, oh, wait, so I have a -6. So I need the +6 divided by the 1 sulfur that's there. So this sulfur is +6. We know oxygen is -2. So now to determine the charge on the lead sulfate, if sulfate is a -2, we know that, we know that lead has to be a +2 on that one. Right? Because to equal 0, it's got to be a +2. Over here in water, we know hydrogen is +1 in a compound, oxygen is -2 in a compound. Okay, so now when we look from one side to the other, oxygen was -2 the whole time. Hydrogen was +1. Sulfur. Oh, we forgot one of these. Oh, no, we didn't. Here's our sulfur, and there's our sulfur. Sulfur, +6 both ways. Okay, so lead got more positive. Oxidation. There's 2 leads here. Hold on. So this lead got more negative. That was reduction. Okay. So the element that was oxidized was our elemental lead. And that elemental lead was the reducing agent. The element that was reduced was also lead, but it was this lead. So the oxidizing agent is PbO2. So that one was a little bit crazy. That one was probably one of the harder ones that you'll do. Okay, yeah, I'll go ahead and do the next one because this one can be a little bit rough too. Okay, so this is hydrogen peroxide. We know in hydrogen peroxide, hydrogen is +1, and the oxygen in a peroxide is -1. Over here in water, hydrogen's +1, oxygen's -2. This oxygen is elemental, that is 0. Okay, so when you look at what changed from one side to the other, the hydrogen was the same on both sides, right? But here, the oxygen got more negative. It was reduced. Here, the oxygen got more positive, was oxidized. Okay, so the element that was oxidized was your oxygen, and the whole compound is your reducing agent. The element that was reduced was also oxygen, and the agent was H2O2. Okay, let me just double check that. Let me look at this for a second because that feels really weird. -1 to -2, right? So he was reduced. Yep. Okay, so oxygen in both of those was oxygen was oxidized and reduced, and he is the only agent. Okay, this is a spontaneous reaction. Okay, I don't know if you know, like your hydrogen peroxide, if you leave the cap off of it, it basically decomposes into this and is no longer any good. Okay, so I'm going to skip past this. We're going to move to here. We're going to do the same thing, but we're going to do it without all of those blanks telling us what to do. Okay, so on this one here, this is elemental sodium sitting there all by himself with no charge. That is 0. Here, chloride is the monoatomic ion. He gets his -1 from the periodic table. If I have 2 chlorides, that's a -2. So that iron has to be a +2. Over here, we know in compounds, group 1 are always +1, making the chloride has to be a -1. Here is elemental iron, 0. Okay. So when I look from one side to the next, my sodium got more positive, was oxidized. My iron got more negative, was reduced. So what are we doing here? We're indicating who's oxidized, who's reduced, oxidation states, and label the agents. Okay, so our sodium was oxidized, and our iron was reduced. Our sodium is the reducing agent, and our iron chloride was the oxidizing agent. So on this one, hydrogen in the compound is +1. So I have +2 for my hydrogens. I don't want to keep any of them because there's no charge on the compound. So I need a -2 divided by my 2 carbons that are there. Each carbon is a -1. Okay, so over here, this is elemental oxygen, 0. Here, we know oxygen is -2. Okay, and knowing if oxygen's -2, I have a -4. Right? I don't want to keep any of them because there's no charge on the compound, so I need a +4 divided by the 1 carbon that is there. Carbon is +4. And we know in a compound, hydrogen is +1, oxygen is -2. So from one side to the other, my hydrogens didn't change at all. My carbon got more positive, oxidized. My oxygen got more negative, in both cases, was reduced. Okay, so my carbon was oxidized, and the C2H2 is the reducing agent. My oxygen was reduced, and the oxygen is the oxidizing agent. Okay, so here I've got binary compound. Sulfur is definitely more electronegative. He's further to the right on the periodic table. So sulfur is a -2. His charge from the periodic table, meaning lead has to be a +2. This is elemental oxygen, so it's a 0. Here, oxygen is -2. If I have, right, I have that -4 from oxygen, which means the sulfur has to be a +4. Here, I know oxygen is -2. If that whole compound equals 0, I know lead has to be a +2. Oh, okay, there we go. -2, +4. Okay, so when we look from one side to the next, our lead stayed the same, right? So lead was neither one. Our sulfur got more positive, was oxidized. Our oxygen, in both cases, got more negative, was reduced. So our sulfur was oxidized, and the lead sulfide was the reducing agent. Oxygen was reduced, and oxygen was the oxidizing agent. I hope that's kind of coming together for you. Let's do this one. Okay, so if I'm looking here, I have polyatomic ion, right? So I'm going to pull that out by itself. We know nitrate is -1. So we know the oxygen in there is -2. I have -6 for my oxygens. I want to keep one of them for the charge. So I have -5. I need a +5 divided by the 1 nitrogen that's there. Nitrogen is +5. And we know silver nitrate, if nitrate is -1, that silver has to be a +1. Here I have elemental copper is 0. Here, nitrate is exactly the same on both sides. It didn't change. So those oxidation numbers are exactly the same also. Okay, if the polyatomic ion is exactly the same on both sides, then its oxidation numbers don't change. It's not involved in the redox reaction. Okay, but over here, we know this nitrate is -1, so that means that copper has to be a +1, and silver is elemental silver, 0. Okay, so now when I look at who changed, my silver got more negative, was reduced. My oxygen stayed the same. My nitrogen stayed the same, but my copper got more positive, was oxidized. So what did we say? We said silver was reduced, and that entire compound is the oxidizing agent. Our copper was oxidized, and the copper, the whole compound, was the reducing agent. So that is your basics for redox reactions. Let me check my notes, see if there was something else I meant to talk to you about. We did the info sheet, we did some practice, we did the numbers, we identified. Okay, and I will do a different video on balancing redox reactions. Okay, but let me just pop that other sheet up again. Okay, we have those rules, those redox rules. And if you have not, okay, if you didn't write those down, here they are again. You could take a picture, you could write them down. Okay, we're following those rules to assign our oxidation numbers. Then we decide who was oxidized and who was reduced based on did they gain or lose electrons. And if you were oxidized, you're the reducing agent. If you were reduced, your compound is the oxidizing agent. So I do believe that's all I have to say about redox reactions today. So have a great day.